So welcome to lecture 24. So this lecture is going to be talking about least squares or linear algebraic small tip angle RF pulse design. So up till now what we've been doing is looking at the classical methods for designing spiral pulses, for designing echoplanar pulses, and for designing spectral spatial pulses. And so today what we're going to talk about is methods that have come out more recent efforts in RF pulse design research. And so what we're going to be talking about specifically is an alternative approach to spiral EPI and spectral spatial RF design that's based on a least squares or linear algebraic formulation. Okay, so to motivate this, I'd like to point out some of the drawbacks to the methods, the classical methods that we've talked about so far. So these include the inability to design pulses that are compensated for non-idealities either coming from the scanner itself or that arise just due to the fact that due to different patient properties. So we have spatial B0 inhomogeneities, right? So we talked about the effects of spatial B0 inhomogeneities on spiral, echoplanar, and spectral spatial RF pulses. But we didn't talk about any ways that we can actually correct for those effects, right? Given that you could perhaps measure those, the B0 field, or measure a field map in each subject, how could you then design a pulse that accounts for that field, right? And so today we're going to be talking about methods that can do that. These methods can also account for or compensate variations in spatial B1 inhomogeneity, that is the magnitude of the RF transmit field, or B1 plus as it's called mathematically. Okay, so this is a spatial variation of the strength of the RF field, right? So far what we've been doing is designing these pulses, and we are implicitly assuming that if we put in this certain voltage into the coil, that we will get the same amplitude of the magnetic field that coil generates everywhere in space, right? That's been an implicit assumption in all the pulse designs that we've talked about so far. But that's not really the case in practice, and especially as you go to higher field strengths, even higher clinical field strengths like 3 Tesla, which is a really common clinical field strength nowadays, you get some pretty strong RF transmit field inhomogeneities that it would be nice if you could account for. So then another thing that we can't really account for with the old methods is trajectory non-uniformities, right? So the really obvious case of this is the continuous EPI trajectory, right? So that had a sort of zigzag pattern, right, in KZ-KF space, and it induced these distortions, those opposed nulls, right? If you recall, we had the main null and then these two opposed nulls. And that was a result of the non-Cartesian scanning of K-space, right? And we were implicitly assuming when we designed the pulse that we actually were scanning KZ-KF space in a raster manner. But in fact, we have this zigzag pattern, right? And that induces these non-idealities in the pattern. But maybe if we had a better approach to designing the pulses, we could compensate for that non-uniformity. Another problem with the classical methods is that you have relatively limited control over the excited patterns, right? So sure, you can define an analytic waveform that you want to excite, but you can't necessarily guarantee that the pulse that you design is going to precisely hit that pattern. You also cannot generally precisely control ripple levels inside and outside the pass bands, in the pass band and in the stop band. We also cannot incorporate regions of interest, and I'll show through an example what I mean by a region of interest. But basically, what that is let's say that you are trying to excite a uniform pattern over the body, a uniform flip angle pattern over the body, but because you don't care about air, you'd rather leave the air outside the body, outside of the design problem, right? Because you don't care what your pulse thinks it's doing there. So regions of interest are a way to incorporate that prior knowledge into the pulse design. And furthermore, since the classical methods were introduced, we've had some significant developments in both computing power. So computing power has increased dramatically, right? So the classical RF design methods were introduced in the early 90s, but since then computing power has increased dramatically, and what that means for us is that we can solve relatively large linear algebraic problems in efficiently now in a relatively short period of time. even so fast as that we can actually do it live on the scanner. And the other development is that we've had a lot of development especially in the early 2000s to mid 2000s up till now, in algebraic iterative MR reconstruction. That is the types of exactly the kinds of iterative reconstructions that you've done on the homework so far. So those have really emerged and started to dominate MR image reconstruction, at least in research. They haven't found a lot of applications clinically yet, but they're used extensively in research. Okay, so these advances have led to the emergence of some new ideas for RF pulse design based on iterative or least squares formulations that can offer enhanced flexibility, robustness, and control of the RF characteristics. Okay, so let's jump right into it and actually derive a least squares approach for RF pulse design. Okay, so the least squares approach that we're going to take here is based on a simple discretization of the continuous small tip angle equation. Right? So if you recall from earlier, the small tip angle equation is this. It says that the transverse magnetization at a spatial location r in time t is equal to the integral of the RF times the Fourier kernel, evaluated from, earlier we had minus infinity, but we're going to say that b1 is 0 from time 0 for negative time, up to time t. So time t is the time at which we're going to observe the transverse magnetization. And so it's the Fourier integral of the RF times this Fourier kernel containing the excitation k-space trajectory. And the excitation k-space trajectory then is defined as the integral of the remainder of the gradient, if you guys recall that. Okay, so let's assume then that so that we can discretize this guy, let's assume that the RF is equal to a sum of weighted delta functions, right? So we'll assume that the RF is the sum of all these spikes. So these are going to be spikes that are shifted in time, right? We've looked at signals like this before. This is essentially a comb function, right? Where each comb though has a different amplitude. Okay, so it's going to be these weighted comb functions. It's going to be weighted by the RF magnitude and phase. So b1 of n is a complex variable here that changes from spike to spike. And we also incorporate the delta t, right? The time step between samples. Okay, so capital N here is going to be the number of time points So that's the number of time points in the pulse, and that is going to be equal to, in general, that's going to be equal to capital T, the total duration of the pulse, divided by the time step, right? And so delta T here is what's called the dwell time, and so that's the time between RF samples. Okay, and that's usually on the order of like several microseconds. So on the GE scanners, it's 4 microseconds. On the Philips scanners, it is 6.4 microseconds. In other scanners, you can vary it. Okay. Okay. So, but yeah, it's usually between 1 and 10 microseconds. Okay. So then we have that mxy of r is equal to this weighted sum, right? So we carry down the I gamma m0 from above, and now we just plug in this model b1 of tau into the equation, and into the small tip equation, and because the integrals of the delta functions are just 1, we end up with just this weighted train of samples, right? So it's just the Fourier kernel evaluated at time point n times the RF at time point n. Okay, so that takes care of the time dimension, but now we also have to discretize the spatial dimension, right? So if we evaluate the transverse magnetization at a finite set of locations R sub m, right? So m here is going to index space, while little n here is going to index time, right? Okay, so then if we evaluate that at m at a finite set of spatial locations, then we can stack up those spatial locations into a vector, right? So we can basically take a 2D grid and string up all the columns of that grid into this one vector here, right? So this R0 here might be it doesn't matter which order you do it in, but this could be the transverse magnetization in the top left corner of an image, and this could be then in the magnetization in the bottom right corner of a 2D image. Okay, so then we carry along the constants here before, and now we actually get a matrix of the Fourier kernel, right? So if we just look at one row of this matrix, then this is the Fourier expression for one spatial location, right? You can see that we have R0 here, R0, R0. And then we stack up the RF pulse again also into a vector of time points, right? So then when you multiply this vector times this row, this column vector times this row vector, then we get the transverse magnetization at that location R0. Okay? And so then you note also then that the time points, the time indices here, right? So this is B1 of time point 0 times the kernel evaluated at time point 0, and then B1 of n minus 1 times the kernel evaluated at n minus 1. Okay? So you can stack these up. You can call this guy m, this vector m. We can call this guy, actually we'll also incorporate the constants there, and this guy will be capital A, the matrix A, and then this guy will be a vector B. Okay? And so then the elements of the A matrix are going to be these samples pulled out of this matrix here, right? You can see that the K sub j's and the R sub i's appear in both those expressions. Okay? So now, if we can generate samples of our multidimensional target pattern, and we're going to call that variable m desired of R, so it's this function of space, right? And it's a desired pattern, a desired transverse magnetization pattern. So if we can generate samples of this at the locations R sub m, then our designed pulse should satisfy the following. If we multiply B times the matrix A, that should give us m desired, right? So that should equal this transverse magnetization pattern. Right, so then that is basically the goal of pulse design, is to figure out what B vector, when multiplied by A, will give you m desired. Okay, but this equation in general cannot and really should not be satisfied exactly. So we usually settle for the pulse that minimizes what we call the pulse that minimizes the mean squared error between the product AB and m desired, right? So we can write this function this way. So this is this function psi that we're defining, and this is the function that we want to minimize as a function of B. And this is a measurement of the mean squared error between m desired and AB, right? So this is the L2 norm, and so then you can equivalently write this as a sum over space, over the spatial indices, of the absolute value of m desired at location R sub m minus AB at location R sub m, right? So it'd be like rho m of both of these vectors, right? So when you multiply B times A, you get a one column vector, and you take element m of that, and likewise m desired is already a column vector, and you take element m of that, and you subtract the two, take the absolute value squared, and then you sum over space, and then that is the objective. This is the function that we want to minimize. Okay, so we can solve this analytically, and the minimizer is that our best guess for B is what we call B hat, and that is equal to A transpose A inverse times A transpose times m desired. So this is what's called a pseudo inverse, and we've seen this before in other problems. Okay, so how big are these vectors or matrices approximately? Well, m desired is usually going to be on the order of about 1,000, maybe several thousand, for a two-dimensional problem. So I should state that this is for a 2D problem. Things can get quite a bit bigger once you add some more dimensions here. Okay, but m desired will be about 1,000 by 1. That means that A has to have a row dimension of 1,000, and then the RF points are there's usually about 1,000 RF points too, and the RF is about 1,000 by 1. So it's actually a little bit smaller in practice than image reconstruction problems. It's not an order of magnitude smaller, but it's somewhere between 1 and 10 times smaller than your typical image reconstruction problem. So we can usually solve these problems quite a bit faster than a normal iterative image reconstruction. Okay, so it's more feasible to build explicitly this matrix A than the image reconstruction matrix A, right? So we talked about in the homework how it was very difficult to instantiate an entire image matrix A at a normal spatial resolution, at normal clinical spatial resolution. But it's still better. But it's still better in practice, even though we can usually build these these matrices explicitly in MATLAB or wherever. It's still usually better to use an approach, an iterative solver like conjugate gradients, and then NUFFTs to evaluate products with A and A transpose. Okay, so in the example that I'm going to show today of spiral pulse design, we're going to actually build it explicitly because I intentionally made it a fairly small problem. But in practice, usually what you'll do is use conjugate gradients and NUFFTs. Okay, and as in many least squares problems, you very often use regularization, right? And this is used for the following, can be used for the following applications. One thing you can use it for is limit the total RF power amplification that might happen due to poor conditioning of the problem. So if the problem is a little bit underdetermined, meaning you effectively have fewer rows in the matrix A than you have columns, that is, you have fewer equations than you have unknowns. Then you can add some regularization here to force the solution to be a little bit smaller, right? And so then in that case we get that B hat is A transpose A plus lambda I inverse, right? So then if you take the derivative of this with respect to B and you set it to 0 and solve for B, this is what you get. And this ends up just reducing the magnitude of B, or it generally reduces the integrated power of B, and so that will tend to reduce its amplitude as well. Okay, another thing you can do is you can use a roughness penalty here to reduce waveform oscillations, and that can in particular be useful where adjacent k-space, excitation k-space locations are a little bit too close together. So that means you effectively don't really have too many unknowns, right? And you don't have a way to discriminate what those two unknowns should be. Then what you can do is you can use one of these penalties to effectively force them to be just about the same. And so then that's how you formulate this. So then you have again the least squares function of the excitation error, and then you add on this regularization term here, where you take differences, the absolute squared differences between consecutive RF time points, right? And so when you do that, what you end up with is a solution like this. So then we get that B hat is A transpose A plus lambda R inverse times A transpose M desired. And R here is a finite differencing matrix. So it's called a finite difference matrix. And so what that's going to look like is something like this. It's going to have 1, minus 1, and then zeros up to there. And then it'll sort of continue on down this way diagonally, right? And it will then go to be all zeros up until we get to 1 minus 1 at the end in the lower right-hand corner of the matrix. Right, so when we multiply an RF pulse times this, then we get one point hits there, another point hits there, and that's taking the difference between these 2 points. Right, and then, I'm sorry, that's not quite the right expression actually. This should be R is equal to this matrix transpose times itself. Right? That's what R is equal to. Okay, so but it's still, you can see it the same way. So you take this matrix, you build it, you take its transpose, and you multiply it by itself, and that's the R matrix. Right? Okay, so that's the basic approach. Now, it turns out that this approach is extremely flexible in that we can compensate all kinds of deleterious effects on our RF pulses. So, for example, we can compensate measured off-resonance by modifying the elements of the A matrix to include the off-resonance term that we looked at before in the small tip equation. Right? So you basically also sample your field map. If you acquire a field map, then you sample it at the locations R sub I, and then you also sample time at the time points of each RF pulse sample, and then you evaluate this kernel and you multiply it by the elements of your system matrix, and we'll see that in this spiral example that we'll do at the end of this lecture. You can also compensate measured transmit or RF field variations And so then if you can measure a map like this, and there's lots of different ways to measure the strength of the RF field as a function of space, then you basically multiply the elements of your matrix by B1 by that measured B1 plus field at each location R sub I, and use that as your design matrix. We can also incorporate regions of interest to remove spatial locations from the design problem that we don't care about, or differentially weight different spatial locations, right? If you care a little bit less what happens with the excitation in one area versus the other, that turns out to be a good way to control ripple levels, and we might see that later on, and we'll see that later on for sure in SLR pulse design, but we might also see it in some multidimensional RF design context as well. Okay, so in that case what you do is you reformulate the problem by adding on a diagonal weighting matrix here, W, and the elements along the diagonal of that W matrix are these W sub m's, and each one is a weight that hits the squared error at that spatial location, right? So what you would want to do if you wanted to remove some spatial locations you don't care about, you set W sub m equal to 1 for those locations, and you set it to equal to 0 for locations that you don't care about. Okay, so let's do a spiral example here. So I wrote this up in MATLAB to be an illustrative example of using a least squares pulse design. So this is based on a spiral pulse, and this pulse is going to be 2.5 milliseconds long. The dwell time is 4 times 10 to the minus third milliseconds, right? So this is in milliseconds. And so then the vector of time points is going to be equal to 0 to dt to capital T, the duration of the pulse, minus dt, right? So this will give us 2.5 divided by 4 times 10 to the minus third samples in our RF pulse. The spatial resolution of the trajectory is going to be 1 centimeter, or 1 cycle per centimeter, or that's just 1 centimeter. So then the maximum spatial frequency we're going to reach with this trajectory, that is the maximum k here, is going to be 1 over 2 times delta x, right? So that's 1/2 cycles per centimeter. And you can indeed see that in the plot here, that our trajectory reaches plus and minus 1/2 cycles per centimeter. And we're going to use a field of view of 20 centimeters. And so that means that the number of turns that we should have is equal to k max times the field of view. Right, so what would that give us? That would give 20 times 1/2, that's 10, n equals 10 here then, right? And if you count up the cycles here, or the number of turns in your trajectory here, you'll get 10. Okay, so then we're going to use a constant angular rate spiral in trajectory, and that's given by this analytic equation that we showed in class earlier, right? And so if we do that, then we get a complex vector of points k. The real part of this is the kx axis, and the imaginary part is the ky axis. Okay? And so I've plotted that here. And you can do that in MATLAB whenever you do give the plot command a complex variable. It's going to put the imaginary along the y-axis, and it's going to put the real part along the x-axis. Okay, so now we have a trajectory, and we've defined the spatial grid essentially that we're going to be using for design, or we've determined the field of view and the resolution of the trajectory. Now we have to set up the target pattern and the system matrix. Okay, so what we got to do first is build up a set of discrete spatial locations, x and y, and we're going to use MATLAB's mesh grid function to do this. Right, so you could pull this. All this code that I'm showing today it only uses built-in MATLAB stuff. Okay, so then you can call the mesh grid function, and we want the set of spatial locations to go from minus field of view over 2, so that's minus 10 centimeters, to field of view over 2, that's 10 centimeters, minus delta x over 2, that's the spatial resolution of the target pattern, is delta x over 2. So that's going to be 2x oversampled. If we remove that 2, then we would have a perfect 1x sampling. But now we're going to oversample, so we're going to set our target pattern to be 2 times finer sampled than the resolution of our pulse. And what that's going to do is it's going to prevent our pulse from creating large ripples in the spaces between samples of a 1x oversampled pattern. So that's an exercise you can do yourself if you want to try running this code and removing the 2 there and seeing what you get. Okay, so then the gamma. We got to define the gyromagnetic ratio as well, and so then we set up our system matrix A, right? So this is the A from M equals AB, right? We're defining that A now. So that's equal to 0.001, that's just converting the dt to seconds, times gamma times m0, which we're implicitly assuming is 1 here. Right, we're assuming that. And then, so then times the Fourier kernel, right? So it's 1i times 2 pi. This is the square root of minus 1. That's what I use in MATLAB for square root of minus 1. Times 2 pi times x times the k-space trajectory plus y times the k-space trajectory. And that's it. This one line defines our system matrix. Okay, so then what we need to do is build the target pattern. And so then we're going to call m desired. And this is a 2D matrix right now because it's a 2D image, right? And so then we're going to set it equal to 2 times x squared plus y squared to be less than 5 squared, right? So what this is going to do is it's going to give us an oval pattern, right? So wherever this equation is satisfied, that's going to be 1s, and wherever it's not satisfied, it's going to be 0s, okay? Then I'm going to smooth it out a little bit. So I'm going to smooth it by taking its Fourier transform, and then I'm going to multiply it by a 2D Hamming filter that I've also squared just to increase the smoothing a little bit more. So this is a k-space filter. So what I do there is I build one Hamming vector of a Hamming window, build another identical vector, and I take their matrix outer product, right? It's like 2 vectors like that, and I'm taking their outer product. That gives me a full matrix of these sample points, right? And then I multiply it. I dot multiply that times the Fourier transform of my target pattern. I take the inverse Fourier transform and I get a smoothed out and m desired. Okay. Okay. So then I design the RF, and I do that. I'm going to use a little bit of regularization here. So I just pulled this number out of thin air. I'm using lambda equals 1 here. So this is the RF power regularization that we talked about earlier. Okay, and so here's the line that I'm using to do this, right? So I take lambda times the identity matrix. The I function in MATLAB builds an identity matrix of dimensions n by n, right? So capital N is the total number of points in our pulse. That's equal to the length of the k-space trajectory. And so I just didn't define that variable, but that's what that is. So it's lambda times I times the identity, and then plus A transpose A, inverse of that, times A transpose times m desired. So this is implementing that pseudo-inverse equation that I talked about on the previous slide. And so if I do that, I get this pulse. It's mostly real. It has a small imaginary component. It's really just due to numerical amplification of some numerical noise here, right? So you could pretty much just set that to 0, and you get the same pulse. Okay, so it's mostly real here. So now, of course, we'd like to see what it is that this pulse excites so we can make sure that we actually generated a nice pulse. Okay, so the easiest way to do this, of course, is to just take our A matrix and multiply it by the pulse that we designed. We can reshape it into a 2D image, so we have 40 points by 40 points. That's the size of the X and Y matrices to get our M, right? So we call this a forward projection of the pulse to get the excited pattern. We can also simulate it, right? So I wrote this line here to basically take the k-space trajectory, right? So here I take the differences of the finite differences of the k-space trajectory. I also need to shift it back by half a sample in order to get the timing of the gradients and the RF to turn out correctly. And so then so then that gives me a gradient vector G, right? So this is a complex gradient vector G. So then the real part again is the gx, and the imaginary part is gy. And then I call this faster version of the ABRM function. So it's the same function as you guys have, but I just made it a little bit faster by vectorizing it. That's why I call it ABRM vec. And so what I pass to that is the B1 in radians, right? But multiplying by dt 0.001 to convert that to seconds. And gamma gives me the B1 in radians, right? Each sample is a rotation in radians. And then I give it the gradients, and I give it the x and y locations to evaluate the target, to evaluate the simulation at. So I call that, and then I convert it to excitation, that is to mxy. And then I reshape that into a 40 by 40 2D image, and that gives me my mxy that I've bulk simulated. And here's the results that I get, right? So in radians, this is the linear projection. This is this guy. And this is this guy, okay? So then we can see that they basically agree, right? That's all I just wanted to show here, is that they agree quite well. This is a small tip angle pulse. It's a relatively small tip angle pulse, and so we expect that the patterns that we get are going to agree whether they're cast in terms of flip angle or in terms of MXY, in whether or not they're in, which, it doesn't matter which units they're in. Okay, so that builds our RF pulse for us, right? Our basic, that shows you how to do a basic RF pulse design. But now let's look at what we can do in terms of actually exploiting the capabilities of this method. So first off, I'll talk about an example doing off-resonance compensation. So what we do here is, just as I said before, you build a field map into the system matrix. That is, you build the off-resonance phase accrual due to the field map into the system matrix, okay? So here I'm just building this arbitrary F0 vector, or sorry, this arbitrary field map, right? And so the peak is going to be, actually it's going to be 200 hertz. Here, that's a typo. So then F is just equal to this circle that I shifted off in space, and then I again filter it using the same approach that I showed before for the target pattern. And then I get that back, so it's a little bit smoothed out, and then I multiply it up to 200 hertz, and then I build that off-resonance kernel that I was talking about before. And so you basically have in that kernel the field map, right, as a function of space, so that's along the row dimension, and then times time, which is a row vector, right? So this is a column vector, and this is a row vector. And anytime in MATLAB when you do parentheses and then colon, that gives you a column vector, right? And so then, T was built to be a row vector. So then this gives us a full matrix of the off-resonance phase accrual that we can then build into our system matrix A that we previously defined, giving us the off-resonance, the system matrix including off-resonance. Okay, so right away we're just going to see what happens when we take the pulse that we designed before without off-resonance compensation and multiply it by this matrix and then reshape it to a 2D image. Right, so that is this guy. Right? So you can see here that it's all blown out, right, on this right-hand side where the field map is non-zero. We get this huge blurring effect of the pattern in that area. Okay? But we can compensate this almost completely, right? If we just design the pulse, instead of using the A matrix, if we use the AF matrix, which essentially what we're doing is we're adding knowledge of the field map into the system matrix, right? So we're including that in our forward model, and then we basically solve the exact same problem as we did before for the B1 vector. Here we're solving it using AF instead of A, and that's it. That's the only difference. And then if we see what we get from that, you can see that we've corrected it. This MFC is this guy, and it's basically completely corrected, right? There's a little bit of residual error. And of course, you can't do this. You can't compensate it perfectly if the trajectory ends up skewing so much that you're not covering full K-space in that region. But you can usually compensate it to a very large degree. And so the last thing I want to talk about is incorporating regions of interest, and this is a pretty nice thing that you can do with these methods. So ROIs can provide us with additional degrees of freedom in defining the field of views of our pulses and their resolution. So in this example, what I'm going to do is I'm going to use an ROI to enable the excitation of a higher resolution pattern, right? A pattern that's sharper in one direction, while reducing that direction's field of view so that the overall pulse duration remains the same. Okay? And so what we're going to do here is first I'm going to build a higher resolution excitation pattern. So this is essentially the same code that I did before, but now I am not going to use a full Hamming window in one direction, right? So you notice that here, this is the key difference between M desired and M desired R here, which is that I'm going to take the 0.1th power of the Hamming window along only one direction, right? So this pattern is going to end up being sharper in one direction. Sharper or higher res in one direction. Okay? And then, let's see, I need to define the ROI itself, right? So this is looks a lot like the M desired, right? So it's just going to be ones inside this oval that's bigger than the M desired oval. Okay, so that's our region of interest is also going to be in an oval shape. Okay, so then I design a low-res RF to excite this, right? So I want to see what happens if I take this higher res pattern and I use the original system matrix at a lower spatial resolution to excite it. I'm going to go ahead and incorporate the ROI by making it a diagonal matrix, right? So this is that matrix W that I talked about before. That's that capital W matrix, and that is equal to diag of W sub m, where the W sub m's are literally these weights right here in this vector. I can save a little time by just directly multiplying those weights by my target pattern here, but this is where they enter into the equation. So then I can get the pattern excited by the low res pulse by forward projecting it through the A matrix and reshaping it to be a 2D image. That gives me the low res pattern, right? So this is the pattern that is excited by a pulse designed using the same trajectory we had before, but now trying to excite this higher resolution pattern, right? So we expect it to not do as well. Okay, so now what I'm going to do is I'm going to build another system matrix where I double the resolution along kx, along x, right? So here I'm multiplying the trajectory along the x direction by a factor of 2, and so then that is going to reach a higher spatial frequency in kx, but it's also going to give me a smaller field of view in x, right? Because not only are we increasing the extent that the trajectory goes out, but we are also increasing the gaps between the arcs, right? So it's a higher resolution but a smaller field of view, and that's really why we need the ROI here for this problem. And then we're going to leave the y direction alone, right? So we're trying to excite a sharper pattern in the x direction, and then we take this matrix and solve it just as before with the ROI, right? So it's the same equation as this, but just replacing the A matrix with the higher resolution AR matrix. And then we take MR, we take the forward projection to get the ROI pattern MR, right? The pattern that this B1R excites. Okay, and hopefully it will actually be a little bit nicer looking than this one. And here's what we get. So first I plotted on the left-hand side here the trajectories. So this nice circular spiral is our original trajectory. Then we doubled the trajectory along the kx direction. So you can see that the gaps are half as large along ky as they are along kx. So we have half the resolution in kx. Now really this whole picture should be rotated, right? This whole plot should be rotated compared to here, right? Because in this direction we've actually reduced the field of view vertically. So that's really the x direction here. So I'll make that explicit. So this is the x direction and this is the y direction in the images, but that's rotated in the k-space plot. Here is the low-res M desired. This is what we've been trying to target with all of our previous pulse designs, so it's got nice smooth edges. Here's the higher res one, so you can see it's smoothed out a lot in this direction, in the y direction, but not nearly as much in the x direction. And so if we try to excite that pattern using the low-res RF that has the full field of view but is a lower resolution everywhere, then you can see that we get these large ripples in the pattern, and that's because it can't quite, the RF pulse can't, the trajectory can't quite support the relatively rapid transition in this direction that you have to make between no excitation and full excitation in the middle. Right, so it's not a high enough resolution to make that jump without a lot of rippling, and so that's why we get these bright, dark regions, interleaved regions inside there. So we call those ripples, right? But you can see that we don't have much excitation anywhere outside of the targeted oval, right? So this is a full field of view pulse, so it doesn't target much. It's higher excitation than we had before because we included the ROI, but it's still not a lot, especially compared to the high-res RF, which excites a lot of junk outside the ROI, right? So if we were to draw the ROI on here, it would look like this. It would be, this is what the ROI looks like roughly. And so outside of the ROI, any excitation is fair game, right? The optimization can put anything it wants out here as long as it gives us an accurate excitation in here. And you can see that indeed the pattern is a lot sharper in this case, right? And the rippling is a lot lower when we actually modify the trajectory this way and use the ROI to give us to give us the reduced field of view in the y direction or in the x direction. Okay, so in the end we get lower ripples in the high-res RF pattern, so we've used the ROI to do something useful. Okay. So to summarize, algebraic RF design, algebraic or least squares RF design, is got a lot of flexibility to it. It's got a lot of power to it, and so it's trajectory agnostic. It doesn't care what k-space trajectory you put into it. It's not based on any one trajectory, so you can put anything for k that you want. It's up to you to make sure that that k fully samples k-space, right? It provides us with a lot of flexibility that is not provided by classical methods that we've talked about so far, such as the ability to compensate B0 inhomogeneities, the ability to incorporate ROIs. We can even do T2 relaxation or T2 star relaxation, build that into the system matrix. So we basically try to perhaps put more excitation at the end of the pulse if we can. If we have that kind of flexibility in the trajectory, you can actually model that in the system matrix, and then you'll get a pulse that will give you the best pattern subject to including decay, T2 decay, for example, in the system matrix. It also allows us to use regularization, which we didn't explore as much in these examples, but there's all kinds of different ways that you can regularize the pulses that you design using this method to give you certain kinds of characteristics. So one example of that, one paper that I wrote about this, is I actually regularized the envelope of the RF. So it turns out that some cheaper RF amplifiers have a very difficult time with rapid changes in the envelope of RF pulses. Yet these kinds of amplifiers are the kinds of amplifiers that you'd want to use if you had a mini-channel transmit system, right? And so what we can do then is to encourage pulses to encourage our pulse designs to yield pulses with fewer rapid changes in the envelopes, right? So you can imagine that this pulse has a lot of rapid changes in its envelope, but we might like to instead have a pulse that gives us something more like that, right? So I actually came up with a way to regularize the envelope of the RF pulse, right? And so I was able to get pulses that then subsequently gave a more accurate excitation pattern because the amplifiers didn't distort them as much, okay? So these methods also, if you're going to use these methods, as we've done in class, we've introduced the classical approaches first. It's really important to understand those approaches first if you're going to be successful in implementing these approaches. That is, if you're going to have a realistic idea of what is possible with these algebraic pulses, it's really important to have a good grasp of the classical approaches, which we've gone over here. Usually, as I've said before, we use NUFFTs in the conjugate gradient algorithm to design these pulses. And here we've used a least squares formulation, right? But you could also imagine using performing a linear algebraic pulse design using a constrained optimization, right? So you could imagine designing a pulse that comes within a certain delta value of the target excitation pattern, right? You could reformulate it that way, and there might be different ways to do it. You could have hard RF power constraints. You can say, I want the minimum excitation error subject to hard constraints on the magnitude of the RF pulse. Different things like that. So there are different ways to do it to formulate the problem that would still fall under the umbrella of algebraic RF pulse design. Okay? All right, so that's all. Thanks.